Okay, so it's actually really good that the two previous speakers were before me because motivated a lot of the stuff I'll be talking about. The work I'll be talking about is work that I did with my PhD student, Feng Chu, who just recently graduated. Okay, so a brief outline of the talk is as follows. I'll first just give a motivation, which the other two speakers have already gone over. Our goal again here is to try to estimate or to try to construct confidence intervals for quantiles. And the basic approach that we're going to be using is to exploit a Bahadur representation. So I'll first review a little bit about what is a Bahadur representation in the case of crude Monte Carlo. And we were able to extend this idea of a Bahadur representation for different variance reduction techniques. And so what we actually did was we developed this very general framework that holds for a large class of different variance reduction techniques, and I'll describe exactly what that framework is. I'll talk a little bit about the specific example of importance sampling, which also fits in our framework. And then I'll give you the asymptotic results that we established. So the Bahadur representation, it turns out that a Bahadur representation also implies a central limit theorem, and it also allows us to estimate the variance constant in the central limit theorem, which is the key thing that we wanted to do for constructing confidence intervals. I'll then give you some empirical results on just a small simulation example and give you some conclusions. Okay, so as the other people have said in this session, a quantile basically is defined as follows. So suppose that we have a random variable x that has a CDF capital F. We're interested in computing the p quantile, which is defined to be the generalized inverse of the CDF evaluated at p. Right, so here's just the pictorial representation of what the p quantile is. And as other people in this session have mentioned, there are many different applications of why you want to estimate quantiles. And one example might be in project planning. You want to figure out exactly when is your project going to complete, or you'd like to give a date when you think your project is going to complete. So perhaps maybe what you'll give is a 0.95 quantile of the project completion time. Also, as mentioned by the first speaker, quantiles are known as value at risk in the finance world, and they're often used to measure the risk of portfolios. So what's the typical approach for estimating a quantile using simulation? The typical approach is as follows. What we do is we generate n samples. And then from our n samples, what we do is we compute an estimate of the CDF. So let f hat n be the estimate of the CDF. In the case of crude Monte Carlo, what do? We just generate n samples from the original distribution in an independent, identically distributed fashion. And then we calculate the empirical CDF, which just assigns mass 1 over n to each one of the sample points. Now, since the true quantile is the inverse of the CDF evaluated at p, a natural estimator of the quantile using simulation is to invert the estimated CDF. So now what we'd also like to be able to do is to give a confidence interval for the quantile. And the typical way that we're all familiar with for developing a confidence interval is first what we do is that we show that our estimator, point estimator, satisfies the central limit theorem. So here's a central limit theorem that we might have for a quantile estimator. And in the case of, so here, kappa p squared I'll denote as the asymptotic variance that appears in the central limit theorem. In the case of crude Monte Carlo, what we have is that kappa p is square root of p times 1 minus p divided by the derivative of the CDF evaluated at the true quantile. Okay, so this is what the last speaker was mentioning. And so if we can actually come up with a consistent estimator of kappa p, then we can construct a confidence interval by basically kind of unfolding the central limit theorem, which is just the standard approach that people use. Now, as mentioned before in the last few talks, in general, crude Monte Carlo might not be very efficient for estimating a quantile. And that's especially the case when we're estimating extreme quantiles. So when p is close to 0 or close to 1, we might have very wide confidence intervals. So there have been a number of different variance reduction techniques that have been proposed for more efficiently estimating quantiles. And those techniques include importance sampling, a combination of importance sampling and stratification, control variates like Latin hypercube sampling, and so on and so forth. And so here are a bunch of references that develop these different ideas. So it turns out that all these different papers up here actually proved central limit theorems for their quantile estimators. Okay, but none of these papers actually gave a way of consistently estimating the variance constant that appears in the central limit theorem. Okay, so the main focus of our work was actually how do you estimate this variance constant. Okay, and so we were actually able to come up with consistent estimators of this variance constant. And our approach was basically based on this so-called Bahadur-Ghosh representation. So let me just go over briefly what the Bahadur representation is. So let me just kind of give you kind of a heuristic argument about how you what a Bahadur representation says. So let's assume that the derivative of the CDF at the true quantile is positive. And so that it essentially assures that the CDF is strictly increasing at that point, and so we have a unique there's a unique quantile. In the case of crude Monte Carlo, what we had again before was here's our empirical CDF, which just assigns mass 1 over n to each of the samples. So roughly speaking, we can say that the empirical CDF should be close to the true CDF. And since we invert the true CDF to get the quantile, what we're going to have is that the estimated quantile should be close to the true quantile. Okay, so then we also have that if we evaluate the CDF at the true quantile, that's basically equal to p. So let's now replace the true quantile with its estimator. So we get this first approximation. Now what we do next is let's just use a Taylor series approximation centered at the true quantile. So we have this term plus this kind of first order term over here. That's the derivative of the CDF. And now let's replace the true CDF with the estimated CDF over here. Okay, so now let's just look at the first equation, p, and the last equation. Now what we can do is just rearrange terms. And so what we do is let's bring this f hat over to the left-hand side and then divide through by the density function over here, evaluated at the true quantile. And so what we get over here is this kind of Bahadur representation. So the Bahadur representation says that the quantile estimator is approximately equal to the true quantile plus this linear transformation of the CDF estimator evaluated at the true quantile. Okay? So this is a kind of rough derivation of this Bahadur representation for crude Monte Carlo. And it turns out that you can make this argument rigorous. And that's basically what Bahadur did in 1966. And so what we do is we take this approximation over here, we add on this remainder term. And so what Bahadur showed was that the remainder term goes to 0 at some kind of almost sure rate over here. Okay? And so what he had to assume was, let's assume that the derivative of the CDF is positive at the true quantile, and also that the second derivative of the CDF actually exists. Ghosh was actually able to come up with, to prove a similar type of result. Instead of showing that the error term, this remainder term over here, instead of establishing an almost sure rate at which it goes to 0, he just showed kind of a weaker version, where square root of n times this remainder goes to 0 as n goes to infinity. Now, he also required weaker assumptions than what Bahadur assumed. So he only Ghosh only required that the density function at the true quantile was positive. Okay. Now I should also mention that we also make another, I guess, transformation here is that instead of looking at a fixed value of p over here, we actually allow for a perturbed value of pn. Okay, so let's let pn be basically this fixed value of p plus some perturbation of order 1 over the square root of n. Okay? And so now this Bahadur representation over here allows that we have this perturbed value of the quantile at a perturbed value, again, is equal to the true quantile plus this linear transformation of the CDF estimator at the true quantile plus the remainder term. Okay? So here's this Bahadur representation, and this is going to be the key for letting us derive confidence intervals for our quantiles. So one other thing that I should mention about these Bahadur representations is one reason that they're interesting is that they give a lot of insight into why quantile estimators actually satisfy a central limit theorem. So one way of saying this is just if we look at this first equation up here, if I just bring the true quantile over to the left-hand side and scale up everything by the square root of n, then what we see on the right-hand side is square root of n times this thing over here. But this thing over here is just the sample average that's transformed linearly. And so the right-hand side over here is going to satisfy essential limit theorem. So therefore, the quantile estimator is also going to satisfy essential limit theorem. OK, so now, as I said, we developed this Bahadur-Ghosh representation for variance reduction techniques. So what we needed was a set of assumptions on the estimated CDF when we're using a variance reduction technique. Okay, so here are the assumptions that we required. So the first assumption was that our estimated CDF, what we required is that the probability that the estimated CDF is monotonically increasing in x, that has to converge to 1 as n goes to infinity, as the sample size gets larger and larger. So notice that we actually allow for the estimated CDF actually may not be monotonically increasing. And that's actually the case that occurs, or can occur, in the case of control variates. When you're applying control variates, the estimated CDF actually doesn't necessarily, you're not necessarily guaranteed that it's going to be monotonically increasing. However, it does turn out that in the case of control variates that the probability that it's monotonically increasing will converge to 1. The second assumption that we need is we looked at what's the probability of a sample under the original distribution lying in an interval of length 1 over the square root of n. Okay, so we're looking at this interval of length 1 over the square root of n, where one of the endpoints of that interval is the true quantile. Okay, so here's the probability that a sample lies in that interval of that length, right? And then we subtract off the estimated probability that we get from estimating our CDF using our variance reduction technique. So if we take the difference of those two things and scale it up by the square root of n, that needs to converge weakly to 0 as your sample size gets large. And then the third assumption that we needed is that the estimated CDF at the true quantile needs to satisfy essential limit theorem. Okay, and so the essential limit theorem is over here, where we have that psi p squared is the variance constant in this essential limit theorem. So what we actually showed was that these three assumptions over here actually hold for various different types of variance reduction techniques. So we showed that it holds for importance sampling by itself. It also holds for stratification by itself, or a combination of the two. Also holds for antithetic variates and control variates as well. OK, so this is just kind of a review of some of the other previous speakers' slides. So I'm going to go over this fairly quickly. So one possibility of a variance reduction technique that we could use is importance sampling. And so this was proposed by Glynn in 1996. So again, we have f is our original distribution. We need that f is absolutely continuous with respect to this new distribution, f star. That's what we're going to use. Sample from f star, generate samples from f star using when we're using importance sampling. We have L over here is the likelihood ratio. And so we just do this change of measure type of argument that we've all seen before, right? So here's f of x, the true CDF evaluated at x. We can express it as an indicator function times integrated with respect to the true CDF. We introduce the likelihood ratio and do a change of measure. And so now what we have is that the true CDF evaluated at x is equal to the expectation under the new measure of the indicator function that a sample is less than or equal to x times the likelihood ratio. So this suggests how do we then draw samples, or how do we then estimate the CDF using this representation? This suggests why don't we generate samples of x from f star and then compute the indicator function and then multiply it by the likelihood ratio. So here, as the other speakers have shown, is our estimated CDF when we're using or I should say an estimated CDF when we're using importance sampling. And so what we get next is we invert this estimated CDF to come up with a quantile estimator. And so we're actually able to show that the assumptions that I mentioned before actually hold, the three assumptions that I mentioned before actually hold for this importance sampling type of quantile estimator, as long as we have the following condition hold. So we need to have that the expectation under the importance sampling measure of the indicator function of a sample being less than or equal to the true quantile plus some delta times the likelihood ratio to the 2 plus epsilon power, that needs to be finite for some value of epsilon and delta that are positive. So I should mention here that, as I said before, once you have a Bahadur representation, it typically implies a central limit theorem as well. So what we'll have is that the quantile estimator is going to satisfy a central limit theorem. So Glynn has actually also provided a central limit theorem for quantile estimators. He used a very different approach. He used, his approach was based on, what are those called? Variance-reduction result. And so what he actually required was a finite third moment. And so we were actually able to relax that assumption using this different approach. OK, so here now is the first result that I'll mention. So we have the assumptions are as follows. We assume that the derivative of the CDF is positive at the true quantile. And we need to have that our CDF estimator satisfies our three assumptions from before. Now what we can do is we look at the estimator of the Pn quantile, right? So we have this perturbed value of P over here. And so now what we get is this Bahadur-Ghosh type of representation. So rather than the strong representation that Bahadur established, we're working with the weaker type of result that Ghosh had established. So over here, what we have is that the square root of n times this remainder term converges weakly to 0. So I should mention that, well, pretty much after we finished all of this work, we then found out that some other people, Sun and Hong, had actually proved an almost sure Bahadur representation for the case of importance sampling. But they actually require stronger assumptions, and they only look at the case when Pn is fixed at P. Okay? But now for us, in order to establish confidence intervals, it was actually important that we actually had Pn to allow Pn to actually be a perturbed value of P. OK, so as I mentioned before, one result or one conclusion of a Bahadur representation is that we have that the quantile estimator then satisfies a central limit theorem. OK, so here's the central limit theorem that we have for the quantile estimator. So this is a central limit theorem for basically any one of those variance reduction techniques that satisfy our three assumptions that we mentioned before. So this central limit theorem over here for the quantile estimator, again, has this variance constant kappa p squared. OK, so now it turns out that kappa p squared has the following form. So kappa p we can express as the ratio of psi p divided by the density function evaluated at the true quantile. Now psi p over here is going to be exactly the variance constant that appears in our central limit theorem for the CDF estimator evaluated exactly at the true quantile. Okay, so that's exactly what we saw before in our assumption A3 over here. So psi p is exactly that variance constant that appears in that central limit theorem. Okay, so now once we have a central limit theorem, if we can actually come up with a consistent estimator of kappa p over here, then we can come up with a asymptotically valid confidence interval. Okay, so what we want is consistent estimators of the numerator and the denominator. And it turns out that estimating the numerator is fairly straightforward, and it's actually the natural estimator that you might come up with for the numerator. You can prove that it's consistent, and that's what we did. But it turns out that the denominator term, the density function evaluated at the true quantile, that's the more difficult term to estimate. And Peter, in his paper on importance sampling for quantiles estimator, said that this is actually the major challenge to constructing confidence intervals. And Glasserman, Heidelberg, and Shahabudin actually said that this is actually a difficult problem. So, but we were actually able to figure out how to estimate this quantity, 1 over the density function evaluated at the true quantile. So let's let phi p be this 1 over the denominator term of this variance constant that appears in the central limit theorem. So it turns out that phi p over here, just by using a simple chain rule of calculus, we can express phi p as equal to the derivative of the pth quantile with respect to p. So since we have a derivative over here, there have been different ways of estimating derivatives in the simulation literature. So one natural way of trying to estimate a derivative is to use a finite difference estimator. Okay? So what we have is, let's use a finite difference estimator to try to estimate phi p, this derivative over here. So what we do is we replace the true CDF with its estimated CDF, f hat n, and then we evaluate the inverted CDF, the estimated inverted CDF, at 2 different values that are basically p plus or minus c times 1 over square root of n. Okay, and then we divide by the length of the interval that we're taking the difference of. So it turns out that this type of estimator, this type of finite difference estimator, has actually been proposed before in the statistics literature. But it turns out, and then in the statistics literature, they've actually proven that this type of estimator is actually consistent. And I guess this should actually be a hat rather than a tilde. And so in the statistics literature, they've proven this type of consistency of this estimator in the case of crude Monte Carlo. But it turns out that their proof arguments don't generalize when you go to variance reduction techniques. And so we actually required a different type of approach to try to prove the consistency of this estimator. And so as I mentioned before, our estimators, the way that we proved consistency of this estimator was by using this Bahadur representation. Okay, so here was our estimator of this finite difference estimator of 1 over the density function evaluated at the true quantile. So this corollary says that it converges weakly to the true value that we want it to. Okay. So again, so here is our finite difference estimator. So it's actually once you've established the Bahadur-Ghosh representation, it's actually fairly straightforward to actually show that this is consistent. So let's just think about why this is actually a consistent estimator, right? So basically what we have is this finite difference estimator over here. This is the estimated CDF, and we invert it at 2 different points. But since this is basically a quantile, this is basically the p plus c times n to the minus 1/2 quantile. Right? So because that's just a quantile estimator, it satisfies a Bahadur-Ghosh representation. And similarly, the other term over here also satisfies the same Bahadur-Ghosh representation, but with a different remainder term. Okay. But now the key is that in this Bahadur-Ghosh representation, I should mention that there was this parameter c over here, which was kind of our smoothing parameter that we used in our finite difference over here. Basically, it only appears over here. And so if you were to use this Bahadur representation in this first quantile estimator and then also in the second quantile estimator, basically most of the terms over here are going to drop out. All you're left with is what's over here. Okay. But now what we have is, so this is the term that we wanted to converge to. What we have over here is the square root of the sample size divided by 2 times what I call the smoothing parameter times the difference of these remainder terms. But since we've established the Bahadur representation, square root of n times these remainder terms go to 0, and so therefore we get convergence. We convergence to what we wanted to converge to. Okay. So let me now just present some empirical results on a very, very small example that we ran, that we did coverage experiments on. So here is just a very simple stochastic activity network. It has 5 activities, 1, 2, 3, 4, 5. And we assume that the activity times on each of these edges over here are IID exponential with a mean of 1. And the goal here was, you can think about this as being tasks over here. Each of the arcs represent a task. And you have this kind of precedence relationship. I can't start activities 2 and 3 until activity 1 has finished, for example. So the time to complete the project is determined by the longest path from starting in S and ending in T. And so what we were interested in trying to estimate is the 0.95 quantile of the longest path from S to T. And so the way that we ran our experiments was to use, to try to estimate this 0.95 quantile using this combination of importance sampling and stratified sampling. I should mention that this combination before, as I mentioned before, was previously given by Glasserman, Heidelberger, and Shahabuddin in a paper. The first thing is, well, how do we actually apply importance sampling on this problem? So the way that we apply importance sampling on this problem is that we used a mixture of exponentially tilted distributions. And this was basically using an idea that Sandeep had proposed with others in a paper. And so basically there are 3 paths in the network that go from S to T. We can either take 1, 2, we can take 1, 3, 5, or we can take 4, 5. Okay, so there are 3 paths through this network. So the idea here was, the idea that they used was, why don't we use a mixture of exponentially tilted distributions, where in the mixture, each distribution in the mixture corresponds to basically exponentially tilting one path, and then leaving all the activities not on that path, leaving them as with their original distributions. Okay, so we have 3 different paths over here, so we use a mixture of 3 different exponentially tilted distributions. So now the question is, well, how do we choose the tilting parameter in each one of those mixed distributions in the mixture. And so the way that we do this is using this idea based on large deviations theory that Glynn had developed and was actually mentioned before in the last talk. And then also, in addition, we're going to use stratified sampling as well. And so what we're going to use as a stratification variable is the path with the largest mean. So basically, since everything over here is IID exponential 1, we have that the path that goes 1, 3, 5 has a larger mean than the other two paths. And so we're going to use that path 1, 3, 5 as our stratification variable. Okay. So I'm not going to go into much more detail about that, but here are just some the empirical results that we got from running some coverage experiments on that small example. Okay, so what we have over here is on the horizontal axis we have the sample size n, and on the vertical axis what we have is the coverage of the resulting confidence intervals. Okay, so our goal here was to construct confidence intervals that had nominal coverage of 0.9, and so what we did was we estimated the coverage from using 10,000 independent replications. So what we can see over here is, I should also mention that all these curves over here, basically, as n gets larger, what we see is that the curves basically seem to be converging to 0.9. So this seems to validate our asymptotically valid, that the confidence intervals are actually asymptotically valid. I should also mention that, as I said before, in our algorithm over here, our finite difference estimator of basically the denominator term in the variance constant in the central limit theorem, we have this extra parameter c that the user has to specify, and we call this some people call this a smoothing type of parameter. And so what we did over here was we experimented with different values of c to see how that affects the coverage that we get. And so what we see is that for these 4 different values of c, we get these 4 different curves over here. But in every case, what we see is that the coverages seem to be converging to 0.9. Okay. So my last slide here. So what we did in this, let me just kind of recap what we talked about here. What we did was we developed this general framework to construct asymptotically valid confidence intervals for quantiles when you're using variance reduction techniques. So I mean, although the focus of this workshop is largely on rare event simulations, this actually holds more generally for any kinds of variance reduction techniques that for not necessarily rare event type of problems. And so we established that our framework holds for this combination of importance sampling and stratified sampling. It also holds for antithetic variance and for control variance. And as I mentioned before, the approach, the key idea for proving the consistency of our variance estimator from the central limit theorem is this Bahadur-Ghosh representation. And so we established this Bahadur-Ghosh representation for quantile estimators satisfying variance reduction techniques within our framework. So that's it. Yes.
The inverse of density estimation, you have this exponent of n was -1/2.
Right, yeah.
Is that optimal in some sense?
Unfortunately, okay, so this is actually a really good question. It turns out that with our Bahadur-Ghosh representation, we were only able to prove that this is consistent for exactly n to the -1/2. For any other value of any other rate of n, it doesn't work. And it turns out that in the crude Monte Carlo case, they actually prove it to prove the consistency of this type of estimator, they can actually work with other powers of n as well. So that's something that it's inherent in the fact that we're using this Bahadur-Ghosh representation to establish the consistency of our result.
Any other questions? All right, so let's speak again.